So guys, we will study these are important topics for interview preparation, especially Reynolds transport theorem and continuity equation and Euler equation. So this video will be a little longer, but I'm damn sure once you will prepare this much video, you'll be able to answer all fundamental questions from fluid mechanics. And when they ask what is your interested point, I mean in which topic you are interested to present your interview, then you can mention gas dynamics some topics or aircraft propulsion some topics. If they're asking two subjects, then you can also mention that fundamentals of fluid mechanics, there you are comfortable with the equations. So these equations I will explain you here in detail. This video will be a little longer, I don't know, it will be 1 hour or 2 hour, let's see, but I will clear everything so that once this much is done, you don't have to run here and there for any other objective. Okay, so what is the intention of this video? In this video I will explain in detail what kind of question will be asked to you regarding Reynolds transport theorem or continuity equation, that is mass conservation, or how to prove them. So different types of mass conservation we'll see here, and Euler equation we'll see here, and very interesting, and also Stokes theorem, Green's theorem, those things also I have covered in this part. So let's start. So guys, why do we study Reynolds transport theorem? Because Reynolds transport theorem will tell you one equation. In that equation, capital N will come. That capital N, if you will replace with mass, then that equation will become mass conservation equation in differential form, sorry, in integral form. And when that N you will replace with mass into velocity, that is momentum, then that equation will become momentum conservation. And if that N you will replace with total energy, then it will become energy conservation equation in integral form. It means Reynolds transport theorem gives you an integral form of a property which is extensive property. Extensive property means which is depending on mass. We have two properties, one is intensive, one is extensive. Intensive properties are independent, so there is a trick: intensive, independent. So IN, intensive property, independent property. But here capital N will be a property which is extensive property, which means which is depending on mass. So what is the key idea? When mass transfer from one place to another place, means suppose mass M is this much amount, it is here, now it is started transporting from here to here, then it will interact with the surrounding, correct? So how any property capital N will change? It will be change or it will be conserve. Okay, so it depends. For example, mass is conserved, that is our consideration. So if we consider that mass is conserved, then what changes we will make in the final equation so that it will convert into mass conservation equation. In same way, momentum conservation equation and energy conservation equation. So let's start with Reynolds transport theorem. So guys, in Reynolds transport theorem, you see this capital N is our main thing, that is the total amount of any extensive property in a given mass. Then we will define eta. Eta is the amount of capital N but for per kg, means capital N is total mass, property belongs to total mass, but eta is the same property what N is, but eta is defined for per kg mass. It means what? Eta is equal to N divided by M. M is the total mass, N is the total extensive property. So this value is your eta value. So that's why one step is written here. If you check, that step is N is equal to integration of eta dm. Okay, because we are, if we will integrate eta for entire mass, then we will again get capital N value. Okay, now how we wrote this triple integration? Guys, mass we can write density into volume, correct? So that's why the rho is coming as density and volume is 3D. Okay, so here whatever integration we had for mass, that will become for volume also. So that volume is dV. So here I have written dV. This dV part is volume integral. Because of that we have three integral signs. In short, this three integral we can represent only by single integral by writing V here. So that's why the last term, single integration volume density eta into dV. So remember, this is the N value. Once this M value is done, then we go for, and also we have to define in our equation what was your dm. So dm was incremental element of mass, and dv is incremental volume of the element. And why are we defining these two? This they can ask in your interview. So when mass is transporting from one place to another place, is there any change in the mass, if the mass is increasing or decreasing. So in the beginning itself we considered our mass is increasing, but in reality mass is conserved. So that's why in the last, when we will derive the equation, there we'll substitute dm is equal to 0. I mean there is no mass created. Okay, I'll come to that, but here symbols you understand. Okay, so just have this note. This shows how the material derivative of any extensive property transforms from a control mass to control volume approach. It means what? Reynolds transport theorem says how you can connect control mass to control volume concept. Okay, now you understand what is dn by dt. This n is the extensive property that is also known as total or substantial derivative. Okay, now here I have taken two diagrams. Diagram A says, you can see this is diagram A. This is at any time t, mass was occupied only in this much region. Then after some time at t is equal to del t time, the same mass reached here. It became like this much. So you can see volume distorted. Okay, so when t is changing, t plus del t plus again t plus 2 del t again t plus 3 del t, so this mass is changing its position and it is interacting with the surrounding. Now we have to pick one intermediate step where the zone B was little inside of zone 1 of zone A. Okay, it means what? This was the initial condition at time t is equal to 0, but at any certain time we consider t plus del t, zone B reached here. Okay, now in this zone A and zone B, you can see some zone is still in common. That zone could not go outside, still it is trapped in. So we have divided our zone A and zone B like this: 1, 2 and 3. It means you can see this zone A we can divide in part 1, part 2, correct? In same way, zone 2 also we can divide in part 2 and part 3. So you can see part 2 is common for zone A also and zone B also. Okay, but you understand the physical meaning. So here this figure shows control mass for small time del t is overlapping in region 2. Okay, why are we saying as control mass? Because only that much mass we are studying. In that zone whatever mass is coming, it means only this much mass we are studying. That mass is shifting, that mass is transporting. Okay, all right, let's go ahead. Now again I have written a note: material derivative dn by dt is the time rate change of property computed as mass moved around. You understood this? We are bothering about any property n which is extensive, so we are trying to understand change in n because the mass is traveling, the mass is transporting, so change in n will come. That change we are saying is dn by dt. So in this expression we will write mathematical meaning of dn by dt. So guys, understand, there was the initial value of n and final value of n. Initial value of n means when mass did not transport, means mass did not travel, when it was here. And another thing is when mass transported, so it will go somewhere else. So that time t plus del t time will come. So n final became at t plus del t time and initial became as t time at t time at t time. So if I'll subtract both the n, then I'll be getting change in n. Divide by time, in how much time it has changed. So that's why this dn by dt I can write n2 plus n3 means part of n present in region 2, part of n present in region 3. You understood na? Region 2 were common and region 3 were outside and region 1 is this side. So this has happened at t plus del t time. This is the final n minus initial n. Again now initial n, some part of n trapped in one region and some part of n is in two region, but at time t. If you are unable to understand this, you go here, check the region again. This, in this, total n is trapped in this. that is initial at t time. So this n will be having two part 1 and part 2. That's why n1 plus n2. But later final after traveling del t time means at t plus del t, this became your new region where zone 2 and zone 3. So n here and n here, n2 plus n3 at time t plus del t. Okay, so we wrote this expression. I hope you are able to understand this expression, n2 plus n3 t plus del t minus final initial one. This guy is final f, this guy is initial, because this guy is at time t and this guy is at t plus del t time. All right, now you understand. Guys, in your interview, suppose you are applying for IISc, IIT Madras, very heavy interview they will be taking. Okay, so you have to be very comfortable with the every step and its physical meaning. Okay, you can let me know if any step is not clear. Just take the screenshot from YouTube and tell me that which step is not clear. I will explain. Send me on WhatsApp. If you are my student already, you will be having my WhatsApp number 6380135260. If you don't have my WhatsApp number, just use this number and send me screenshot where do you have. But I may not reply same day. It depends on my busy schedule or free schedule. Now let's go for, but my coaching students, don't worry, I will reply you immediately same day. Now note, the original confine of mass, that is region 1 and 2, is called here control volume. Okay, now that we are saying as a control volume. Now step 1, we will consider first term, that is region 3. First we will understand what is the meaning of region 3, that n3 term. So first you understand n3 came at t plus del t time, means that much mass came outside, that time t time was t plus del t time. So let's understand very important meaning. How can we write this equation? This equation, guys, it is very easy. I will tell you. Let's understand that here. See, understand. Suppose there is a region, and that region is actually this region. Okay, and you can see here this much part came out. So this part is came out as n3. So that line I'm drawing here. Now I can draw one small area here, on this surface. That area I will say dA. Okay, now you know that there is perpendicular vector to the area, so that perpendicular vector I can say n cap vector. Now when mass is transporting, it may not transport in the same direction of this vector. Okay, I mean to say your vector can go in this direction also. I mean velocity vector can go in this direction. Velocity means with how much velocity the mass is transporting, in which direction it is transporting. So that is my point. So velocity is another vector, and this n is the vector perpendicular to the area. Velocity may not match with this, they can have angle. So let's understand this concept. This v dot n means component of velocity perpendicular to the area dA. Why? Because vector n is the perpendicular vector to the dA. This part is clear. Now you see again, in this velocity vector I have multiplied dA, because you know if you multiply velocity with area, it becomes volume flow rate. So you will come to know that how much increment you have got in volume flow rate, correct? That is dV. Now if in the volume flow rate you multiply density, it will become mass flow rate. So this guy became your dm. Okay, like how much mass increased. Then in that you multiply time, so mass flow rate is nothing but divide by time is coming there because of velocity. Now if you multiply dt, then this t and that dt will get cancelled. So this became the final amount of mass that crossed through that area, dA area. So that much mass crossed through dA area, it means property also crossed through dA area. So how much property crossed through dA area, you multiply eta, because eta is per kg mass property and this much data is your that much mass. So you multiply it, so this became your capital N value only for that much time dt. Okay, so what is this? Amount of n that crossed dA in time del t. Okay, so this total thing is nothing but my n, but not full n. This is only that much n which is crossed in dt time through dA area. So this total became your property n. Okay, so I have written here total amount of n in region 3. This part is done. So we have got one interesting fact here, and you should not forget that about the vector n. Okay, where is your dA area? So you can see here, this is your dA area. I'll change the color, and in this dA area you have taken a vector which is this vector. Okay, means velocity is crossing, I mean your mass is crossing the dA area with that velocity in that direction, but this guy n is this, n is perpendicular to the area. Don't confuse. Okay, v is different, n is different. N has nothing to do with the mass transport. N is rigid and fixed perpendicular to the area dA, but v is the real thing. V is telling you that in this direction velocity is there. Okay, so let's go into more fundamentals. So n3 concept you found. In same way you go for, so guys, don't be blank. You should know what are we doing. We will find out n3, we will find out n2, we will find out n1. We will substitute those things in the equation, main equation, and from there we will assume that okay, if n is conserved, then this will be final equation. Okay, so now in same way we will think for n1. So this is our second major step. So we will consider this variation of n1. I'll change the color. Red will be fine. So if we are considering n1, remember n1 concept is at time t. It is not at time t plus del t. Okay, and guys, one more thing I forgot to tell you. Every time we are keeping del t is equal to 0, limit del t is equal to 0. You can see here also we have written limit del t is equal to 0 because we are writing that del t is equal to 0, because we are understanding what will happen with the property for very small time transport. Del t is equal to 0. Now even this n1, you can see here we are writing in similar way, eta rho and velocity v dot n cap dA. But if you notice here, this is not the same, this is not the same n, this is n cap prime. I will tell you why we are using two different vectors, vector symbols here. In n3, when I was teaching you n3, that time situation was like this, and you understand what was n3. N3 was, here we considered any area, and this n cap was away from the area. But for the calculation of n2, n1 we are considering area here, and this guy is inside, so n prime cap. So this guy is the aerial vector or unit vector perpendicular to area outside the area, but this guy is the vector, unit vector perpendicular to the area, but it is inside area. Okay, so outside and inside, they both, one is outside pointing outside, one is pointing inside. It means they both are opposite in nature. So later in the equation we will substitute n cap prime as minus n cap. Okay, so when you are solving for n1, that time n cap prime will come, and exactly same thing what you have, the way you have found for n3 will find for n1. Remember, 5 terms will come in n3 also, and 5 terms will come in n1 also. Which 5 terms? Eta rho v n cap dA. Okay, and guys, understand, once you will understand this, then write down multiple times, 4-5 times you write down, this concept will be ready. You will be able to solve Reynolds transport theorem, and after that just substitute n is equal to 1, then it will become conservation, momentum conservation, mass conservation, and not n, eta you replace with 1, then eta you replace with v, and eta you replace with specific energy. Then it will become mass, momentum, and conservation, energy conservation equations. Okay, so these things are not for GATE exam, that's why we don't study in GATE class. This is separate. Okay, so then you go for the third term. Third term is interesting here. And all these things whatever I have written here, like n cap prime is the unit normal positive when pointing outward inward, blah 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 blah, just keep in mind, and later we'll substitute. Some static knowledge is there, no need to explain that much. So now the third part, what is the third part? What is remaining now? N1 over N3 over N2 is remaining. So N2 is common for both the regions. 1 2 2 is coming, 2 3 2 is coming. So N2 has two different values at time t plus del t and at time t. So this part was remaining in the equation for N2 and this part was remaining in the equation for N2. So this part we can write as partial differential of N2, because if you have done some basic fundamentals of limit, continuity and derivative in your 11th 12th class, then you may be knowing that this is the formula to write derivative part. Okay, so this N2 is nothing but whatever N is belonging to that middle part in the control volume. So now you know that any N we can write as eta, rho and control volume. So that thing only we are writing mathematically here, and this dou by dou t we wrote outside here. Okay, so now all these three values we will substitute. Now all done. So I have written here notes here. This partial derivative notation is used because the region of integration is fixed and only time t is allowed to vary. Okay, some fancy thing is there, nothing. Now you substitute all the values in the equation, so you understand this part is coming because of n3, this part is coming because of n1. So you can see in this part you have negative sign here, and here you have n cap prime. N cap prime you replace with n cap with minus sign, so this minus will become plus. Okay, and here it will become n cap, I mean the same m what we are having here, same n will come here also. So okay, after replacing this n and this n will become same n cap. Okay, and now interesting part is here. So I have written that what I explained just now. So this part and this part, if you only notice, then you'll understand how much mass is coming out and how much mass is coming in. Now we have taken same vector, so this will become how much mass is interacting with the cross section. Okay, the final surface CS. So this is the entire control surface which is surrounding the control volume, because how much is entering and how much is leaving. So how much is interacting. So that is the final thing. So you can see here everything, eta, rho, v, n cap and dA. Here also eta, rho, v, n cap and dA. All five things we have represented here. But this out and in, surface out, surface in, now we are writing as CS, means control surface. Means we combined both the parts. It means in this equation these two people became only one single person with integration CS, control surface. Which control surface? Inside this control surface you have control volume. Okay, now if you check the last term, we did not change, it is as it is. So this term we got and this term we did not change, this became as it is. Guys, this is your final relation which is known as Reynolds transport theorem. This Reynolds transport theorem, that's all done. If you understood this, if you didn't understand, just practice 2-3 times, you'll understand. Now this is called material derivative, substantial derivative or total derivative. In some textbooks this d by dt is written as capital D by dt. Okay guys, actually we have three types of d by dt. One is dou by dou t, one is small d by dt, one is capital D by dt. In most of the books it is material derivative or total derivative is written as capital D by dt, but here it is written as small d by dt. But don't worry, you just know the physical meaning. Okay, so here what did you understand? This part is a control surface part, this part is control volume part. Okay, all my GIT students are texting this time, this is morning. So I know video is taking longer, but this is only one time you go, that's all done. The rate of change of n the rate of change of n is for a given mass as it is moving around, it is equal to the rate of change of n inside the control volume plus the net efflux. Guys, there is difference between flux and efflux. Efflux means the final exit, exit flux, you can see trick, exit flux, and from control volume. Okay, means how much n is changing inside and how much n is interacting from the outside. Okay, so here I have written as note, this left side term represents the control mass, which says about the change of quantity n within the mass, and it moves with the fluid. And second point I have written, right side is used for control volume. This control volume is not fixed in shape, it can interact with surrounding. It says how n changes within control volume due to the flow of property across the boundary. Now this part over. Now you will make how to write down conservation equation, that is continuity equation, in integral form. Nothing to do, just you know that mass is conserved. So if you replace capital N with mass m, or eta is equal to just 1. Okay, because eta is capital N by m, so it will cancel, 1 will come. So in that RTT, Reynolds transport theorem, you replace n is equal to m and eta is equal to 1. So we already know mass is conserved. Mass is conserved, this we are not getting from RTT. Mass is conserved is different theory. That theory we are applying to RTT. That's why we are putting d mass by dt is equal to 0, because this is our theory. Okay, this is not coming from RTT, right? This is done. Now continuity equation, you can see what we have done here. We have replaced here, and n is equal to mass, capital N is equal to mass, and here 1 and here 1. Okay, so this became final term. So now this became your continuity equation for control volume, and this is your continuity equation in integral form without any assumption. It means this is valid for viscous flow, inviscid flow. This is viscous for rotational flow, irrotational flow, steady flow, unsteady flow. I mean, for everything it is compressible flow, incompressible flow. For everything it is valid. Now, interesting part, in your interview they will tell you, okay, convert this form with various assumptions. So slowly you will start converting. How? The first thing you can do, they will tell you, pakka they will tell you that write down this equation with the assumption of steady flow. So guys, when flow is steady, then something with the time derivative will go 0, because property with time will not change. So dou something by dou t will go 0, so this will be remaining. So this is remaining, that will also be 0, equal to 0. But this part finally became 0 and this part is remaining. So that is the meaning. I mean, this part is remaining, this part went 0, so remaining part we wrote like this. Okay, now they will say, okay, now you write down for one dimensional flow. So guys, for 1D when you write down, then interesting thing you will see, for 1D means for one dimension, this n cap and velocity will be in same direction. So you know that when two vectors you multiply in same direction, you will be getting this same answer. I mean, vector you will lose, like, I mean, I dot I is 1. In same way you will be getting here, because it is now one dimensional, so this also will become like this summation, and this dA will become full A. I mean, I integrate the entire area, and this term is std and 1D, and of course is equal to 0 because that is still coming out. So this is the diagram to explain you what is the meaning of 1D. So it's like there is a pipe, in that pipe you are going in this direction, it is 1D. Okay, and velocity profile I have shown here. This velocity profile also they can ask you in your interview, PhD interview or MS interview. After that, this pattern came. After that, you write rho in, I mean mass in and mass out. So mass out minus mass in, because we considered in that way final minus initial. That's why I'm writing like this, is equal to 0. So this part also you write this side. So this became like this. So if there is only one section where fluid enters and one section where fluid leaves the control volume, then you can apply this. Okay, so you can see mass out is equal to mass in. It means mass flow rate is rho AV, which is constant. So two assumptions we have applied here. One is STD, one is 1D flow. What we did not assume? Compressibility we did not assume, viscous and all we didn't assume. It means what? This equation, final equation, is valid for This equation is valid for viscous, inviscid, incompressible, compressible, irrotational, rotational, for everything. Okay, because those assumptions we are not here. Only this assumption is here: STD and 1D flow. Okay, remember this the velocity what we have assumed here. You remember n cap is not there because we considered velocity and n cap in same direction. It means n cap was perpendicular to area, so velocity is also perpendicular to the area. Okay. Now, as a result of steady flow, the m dot into control volume is equal to m dot out of the control volume. The converse is not always true. Okay, so just leave this, keep in mind. Then we will approach for the differential form just from this. So even this is the differential form because you wrote like this. Now you put d and you differentiate with respect to time or something. So these three terms will come. Then divide by rho av, this term will come. But this differential form they don't ask. Even from this you can write logarithmic form also. You take ln is equal to constant, and then you write down equation. It's morning time, so gate students are asking doubts. After this then we will have a separate way to derive continuity equation. That continuity equation in Cartesian form or rectangular form, and also in polar form. For that we'll make a separate video. You guys can take break, and this is the way to prove. So this format will come. And they have asked to me in IIT Bombay, in IIT Madras, and in IIT Mandi regarding these forms. So that's why I will explain you in detail in the next video.